I am Dr. Indu Yadav, Senior Lecturer, Prosthodontics, Crown and Bridge Department, College of Dental Sciences, BBT. Today I am going to present my lecture on Physical Properties of Dental Materials, Part 1. So let's start. Physical properties of dental materials. Those properties which are based on the laws of mechanics, acoustics, optics, electricity, magnetism, thermodynamics, radiation, atomic structure, and nuclear phenomena are physical properties. For example, hue, value, and chrome relate to color and perception are physical properties that are based on the law of optics, which is the science that deals with the phenomena of light, vision, and sight. Thermal conductivity, diffusivity, and coefficient of thermal expansion are physical properties based on the laws of thermodynamics. Next, mechanical properties. They are a subset of physical properties and are based on the laws of mechanics. So basically, there are following types of properties. Number one, rheological properties. Example, viscosity, thixotropy, viscoelasticity, creep. Second property is optical properties. Physiology of color perception, coordinates of color, shade guides, and shade selection, perception of color. Next is thermal properties. Example, thermal conductivity, thermal expansion, thermal diffusivity, specific heat, heat of fusion, and vaporization. Chemical properties, tarnish and corrosion, types of corrosion. So in today's lecture, which is part 1 of physical properties of dental material, we will cover the rheological properties of dental materials. So let's start with rheology. Rheology, it is the study of flow or deformation of matter. It is important in dentistry because many dental materials are liquid at some stage of their use. Importance of rheology in dental materials. Many materials are mixed as fluid paste which subsequently solidifies. The mixed paste are adapted to required shape. The setting of such materials initially involves a change in viscosity with time. So important rheological properties are number 1 viscosity, second is viscoelasticity, and third is time dependent properties, that is creep and flow and stress relaxation. First is viscosity. So definition of viscosity. Viscosity is the resistance of a liquid to flow. What is the unit of viscosity? It is megapascal per second or centipoise. Resistance to fluid flow is controlled by internal frictional forces within the liquid. Thus, viscosity is a measure of consistency of fluid and its inability to flow. Next, clinical significance of viscosity. Handling characteristics. Second, clinical success of a material. And it can be used to measure the working time of a material that undergoes a liquid to solid transformation. Next, we have to understand how to quantify the concept of viscosity. So for viscosity, we have shear stress tau, which is force upon area. Then we have shear strain rate, which is V upon D. So by definition, viscosity is shear stress upon shear strain rate. So as the shear force increases, velocity increases and a curve can be obtained. Further characterization of the rheological properties of material is obtained by a reference equation. Reference equation says that shear stress is equal to K into shear strain की power n, where K and small n are constant. The constant small n is referred to as flow index. To explain the viscous nature of some materials, a shear stress versus shear strain rate curve can be plotted. First type of fluids are Newtonian fluids. They are also called as ideal fluid. So in the diagram we can see that the red line represents the Newtonian fluid. So in Newtonian fluid, flow index n is equal to 1. So shear stress is directly proportional to shear strain. That's why we get a linear line. Newtonian fluids, viscosity of material is constant and is independent of shear rate. Next we have pseudoplastic fluid. So here again the red line represents the pseudoplastic fluid. In pseudoplastic fluid, flow index value is less than unity. An increase in shear stress produces a less than proportionate increase in shear strain rate. Viscosity is effectively decreased with increasing shear rate until it reaches nearly constant value.